that better? Yeah. Amateur Deep Space Reception by Paul Marsh, M0EYT. The usual housekeeping. I'm sure by now we all know where the fire escapes are and if the fire alarm goes off, etc. So, an introduction to Deep Space Mega DX. The equipment needed and the techniques used to identify extremely weak signals coming from man-made space probes in various parts of our solar system. X-band, or 8.4 gigs, is the primary band of discussion, but Paul will also briefly talk about S and Ka reception equipment and antennas. You can receive signals from spacecraft in excess of 1 billion kilometers with a modest-sized dish in your garden. If you have an interest in EME or microwave weak signal reception, amateur DSR can help you push the limits of what is possible with home-built equipment. Paul.
All right, thanks. Hi, everyone. First of all, apologies for my throat. It's nothing to do with alcohol. It's, there is a genuine excuse. But anyway, so introduction to amateur DSN. These are the areas that I'll be chatting briefly about. A few slides on spacecraft that I've heard. There are a few of them, but I'm not going to bore you to death with hundreds of waterfall pictures. So there's a few highlights and a bit of a discussion about the hardware that you need, as well as the antennas and what have you. So, as said in the intro, primarily we'll be talking about 8.4 gig. There are a couple of other bands which are of interest if you're interested in microwaves. These are 2.2 gig S band, and then the Ka bands mainly at 32, and some near-Earth stuff at 26.5 gig, but that is generally reserved for the Lunar Reconnaissance Orbiter. So, why would you want to do amateur DSN? First of all, if you like fiddling around with stuff and anything to do with weak signal and software-defined radio, then this is an area which is certainly interesting. It does offer some of the challenges that you get with EME, but without the transmit side of things. So there's only half of the system to worry about. You can hear some very weak signals from man-made things that are pretty far away, and as said, get some quite good DX. This is very different from radio astronomy. I'm not listening to noise from a lump of gas. This is something from a man-made spacecraft, which is, for instance, in orbit around Jupiter. There's a lot of people which are interested in amateur DSN, and we have a small community with about 866 other members. So, all of this started at the Marshall Microwave meeting in 2005, and the AMSAT guys here, James and Freddie, had a demo with a very small antenna, 90 centimetre, showing some signals being received off-air from Venus Express and Mars Reconnaissance Orbiter. And because I'm fairly interested in stuff which is coming from satellite, or be it whatever comms you can imagine, this, as far as I was concerned, was the next level. So it's okay having done satellites in orbit around Earth, but I want to hear stuff in orbit around Mars and Venus. So a bit of natural progression. The other thing which hooked my interest was this statement from NASA. And they basically say that our old rubbish cannot detect such weak signals. And no, people who are technical don't like to be told what they can't do. So that was a good driver. So before we talk about the small ground station you can have in your garden, there's a few slides on some of the ground stations that the professional use. This is split into ESA, European Space Agency, and NASA sites, so won't go through all of these, but the crux of the issue here is that the ESA sites have a few antennas, mainly 35 metre, 15, 12 and 3. So this is the sort of thing that you can have in your garden. If I tried to put that up, I'd get a raised eyebrow from the wife, probably.
Only the eyebrow?
Only the eyebrow, yeah. Yeah, she has been accustomed to oddities, shall we say. At the NASA site, so they have 3 ground stations which are spaced at approximately 120 degrees around the planet, and that is, of course, to have fairly continuous coverage from space. and each of these ground stations has a 70 metre. This was originally a bit smaller, about 64, but had additional, I guess, extension petals fitted, a couple of 34s and a 26 metre dish. And these are the antennas which, for example, would receive traffic from Voyager or the Cassini probe before it deorbited, things like this, so where you need high data rates from spacecraft which are fairly far away. So all of these antennas operate in the 3 bands that we've talked about, SX and KA, but NASA are moving towards the 32 gig band, but with that comes a whole world of pain in terms of antenna beam width, pointing precision, etc. So some of the bigger antennas, for example, the 70s, are not used on KA, but the smaller 34s, etc., would be. So some antenna gain figures and some general figures for a typical NASA 70-metre antenna. Maximum uplink power, obviously not going to pretend to read that out, but you can see that's a high ERP. The antenna gain, you know, if you compare this with LF stuff that might have sub 10 dB, you can see that there is a fair amount of gain at mid 8.4 gig. The 3 dB beam width, 0.032 of a degree, so obviously pointing precision has to be adequate. And receiver noise figure, so this is a cryogenically cooled low noise amplifier with about 12 dB, 12 Kelvin of noise figure. So a little bit better than amateurs can attain, but you can still do quite a lot with not much stuff. In terms of frequency stability, so to put it into perspective, if you're trying to receive a signal from, let's say, the Juno spacecraft, you know it is at Jupiter and you know where Jupiter is. You can calculate the as an L, and you know the relative speed between you and Juno, or the spacecraft in orbit around Jupiter, and from that you can determine the Doppler shift, and from the Doppler shift you can determine the frequency. So when you look on your waterfall, you don't want to look in something a meg wide because you simply won't see the signal. You have a span of 5 kilohertz or 2 kilohertz, and at 8.4 gig, you need to be very sure where you're tuning. So the other thing we have, and obviously NASA have orders of magnitude better, are very good quality local station oscillators. In our community, I guess we operate at 10 meg. Some of the NASA DSN sites have interesting oscillators that is not necessarily at 10 meg. Some of them are 100 kilohertz distribution, which is a bit of an odd frequency, but they are distributed via fiber between sites to ensure frequency coherence. And you can see the stability. This is from the NASA paper, which shows you the general deviation over large numbers of seconds. In the amateur world, we can't really get close to that, but you can do things like make a stable oscillator, steer it with GPS, have good time constants, put it in a cool box, make sure the environment around it doesn't fluctuate too much, and you can get down to, you know, a hertz per day or something like that drift, which is adequate. So some of the other interesting data that you can get from the NASA Deep Space Network is this publicly available website, which is called the DSN Eyes, and it shows you an illustration of each antenna and what mission it's talking to. So you can see here DSS-25 is talking to Voyager 2, or 2 antennas are talking to Voyager 2. There's one standing by for New Horizons here. But for us, this isn't much good because we need the proper information as to what NASA's doing, what frequency they're tuning to, where they're pointing. But luckily, this is driven via data that you can quite easily get to. So one of our IRC colleagues wrote a parser for this, and this takes the same data which feeds that lovely graphic and presents it properly. So you can see receive frequency down to a hertz accuracy, the receive signal strength. This is very handy because you can measure your own system and work out what the minimum discernible signal is. And there's various other parameters. So for the DSN Madrid site, you have pointing data, and it means you can slave your antenna at home from Madrid to track as they track. So that leads us on to the antenna pointing section. So we're talking about spacecraft that you obviously can't see. Some of them may not necessarily be in orbit around a planet that you could see through a telescope. How, therefore, do you work out where to point your antenna? And the answer is the online ephemeris tool called Horizons, and that basically is a solar systems dynamics page, and you can type in where you are, your altitude, whether you want an airless refraction model, and lots of parameters I don't understand, but you can tell it what thing you want to track, and it produces this big chart which shows you the time and the date and where to point your antenna, how far away the thing is that you're interested in talking to, and the speed difference between you and the thing you want to track in kilometers per second, which you then use to compute frequency, and then one-way light time in minutes, and that's how long it takes a signal at the speed of light to get from the thing you're talking to your antenna. So in the bad old days at home, this was a bit painful. It was put up temporarily in 2005 and lasted for too long. But the issue here was you had to take the chart, go outside, take 360 off the wanted azimuth because the ring was inverted in terms of calibration, measure the elevation with a precision protractor, point the antenna ahead a couple of minutes, go back indoors, set the RF stuff up, repeat every 3 or 4 minutes. On the day of the Rosetta landing, the weather was miserable, and it was just a miserable experience, having to go out, be rained on, all this stuff. But to catch the signal was worth it. So it has changed a little bit. This is the antenna as it is now. Obviously, this is a sped-up video which shows 1 day's worth of tracking. The antenna here was slaved off a Madrid Deep Space Network antenna as it was doing its mission tracks, which is why occasionally you can see it briefly go off of a target and then come back onto it as they're doing a background noise measurement or something like that. So very nice, fully automated. It's I've become a user now, so I just want to point and click, and I want something to happen. So this has a fairly reasonable degree of pointing accuracy, and more importantly, it works in the rain, and I don't have to go outside and get wet, which is great. So for the ephemeris data we talked about, you can go to the website, type all the stuff in, and it produces lists of pointing data, but it's far easier to write a simple script which automatically does this once a week. So won't go through all of this, but basically it has a list of things I'm interested in, and the script processes it and spits out the data and dumps it on the network drive, and then the machine which steers the antenna takes this data, sets the receive frequency, so it almost is at the point where it is fully automatic. This is at the F1 EHN control panel, so it'll be familiar to those of you that play with EMI stuff, and this is the user interface. So here you can select the object that you're interested in, spacecraft or planet. Here's the ASL readout, and this is where the antenna thinks it is. So you can see that there's 0.02 degree of azimuth error and no elevation error. So very handy, fairly simple to put together. For the receive system, so we'll talk a bit about the microwave front end and how that developed. So in the good old days, this was a very first attempt with a eBay oscillator, and very, very noisy. Phase noise was horrific. With this system, I could just about detect a beacon signal from a geostationary satellite, which is very close. It's almost visible. A lot of work had to be done to get from here to be able to receive some of the weaker stuff. But there obviously are, like any project, numerous iterations of stuff. It's still not in a final state because it's, it needs to be tweaked occasionally to get another 0.1 of a dB of performance out of it, but it does go through various iterations. What you can see on the board here is roughly the same as a block diagram for an LNB you would have on your SAT TV dish at home. This is obviously a homemade version. I can't integrate it to that level, but what is done here is exactly the same as a satellite LNB. Take a high frequency input up in the X band in this case, select which bit of the band you want, either milsat or deep space, have a mixer chain and some synthesized oscillators, and then a reference input from the shack reference, and then the IF output goes to the software radio and the comms receiver for processing. So this is a photo of what it actually looks like, and you can see the usual semi-rigid plumbing and some some microwave filters at the front with some switches, and the two die-cast boxes contain the oscillators, so it's all fairly straightforward stuff. On the front end of the dish, so this would be the equivalent to the front end of the LNB on your Sky system, but homemade version. So there is B&Q 28mm waveguide is used here, which is perfect for X-band, a home-built low noise amplifier, and a Super V4 MA feed, which illuminates the dish very nicely. So here's a shot of the LNA, so it's very good. It's on a par with a DB6NT 8.4 gig LNA, and has got a reasonably good noise figure and a fair bit of gain. And it was a project between myself and Iben in Spain to produce this. I did the mechanics, he did the noise figure optimization. So this is the antenna which is currently in the garden. I'm not allowed for political home reasons to have the extender petals on all the time. The wife doesn't find it acceptable. So I have to have the normal antenna, the 1.8 up most of the time. And then for steering, there was some of these units available a few years ago. They were originally from a warship, and they steered a big EW array around on the side of the boat. But the original use, it's a heavy array of about 100 kilos, and it's the sort of thing that if you're stood next to it and somebody fires an Exocet at your boat, it would knock you over the side because of the rate of turn. And for my application, that was way too high. I want precision rather than acceleration and rapid moving. So there was a little bit of engineering effort required to replace the old motors with integrated gearboxes, and to replace synchro resolver position encoders with current century digital encoders that can talk to the tracker. Very nice hardware. You don't really see many of these on the surplus market. I saw some this year at the Newbury boot sale, but they were £400 to £500 each, which realistically is a bargain considering what you get, but still expensive. So this is the dish at home as it currently stands. I got the kids to dig the hole because they like digging in the garden, so might as well make use of that and say, dig a big hole for a dish to be planted in. So there's a steel pipe, about 6 foot high, which is 1/4 inch wall, and some caps welded on the top and bottom. The antenna can do 360 as by 95 elevation, has reasonable pointing accuracy, and even the wife approves of it. So compared to the previous one, which was a tripod and a mess, she said, oh, well, that looks much nicer. So as far as I'm concerned, that's a win. So also on my antenna, as we mentioned earlier, we will cover a very small amount on KA. It's a difficult band with limited test equipment, so it has a passing mention. But there is this down converter, which can be attached to the front end of the dish. This is 8mm pipe, again B&Q microbore heating pipe, which happens to be perfect for 32 gig, and a big synthesized down converter at the front end. For local stuff out to say 5 million kilometers, you can use a small 60 centimeter dish and get good results. So I thought I'd put a picture of this in. This is the front end amplifier inside the KA LNB. It's very small, so 1.8 by 0.8 millimeters, but it covers our 32 gig band perfectly with a 3 dB noise figure. You might say that is rather high in terms of noise figure, but at 32 gig, that's actually a gift. So it's fairly good. In the shack at home, there is this distribution amplifier. This takes a 10 meg input somewhere from a GPS steered oscillator, and then has a number of isolated outputs which feed software radios, test equipment, down converter, etc. All of them are transformer coupled, so there's no earth loop problems, etc. And it seems to work okay. So From that box which you saw all the microwave plumbing in, the output of that is an IF, so down converted 8 gig, and that generally comes out around 100 to 900 meg, and that's tuned by a AR5000 comm receiver, and the output of that goes to a software-defined radio. Okay, so you'll all be familiar with SDRs. You can see in a particular bandwidth, a peak, and then a waterfall of historic signal. So here, the reason that is not a straight line, but is at an angle, is because of the acceleration or deceleration between my ground station and the spacecraft. So another nice thing about moving everything into the software world is that you can do interesting things to the signal. So you can see here a carrier from the Juno spacecraft in orbit around Jupiter, and this is, I wouldn't say barely perceivable, it's very easy to see, but you can see it is weak. The obvious thing to do with this would be to stack samples on top of each other so you can average the signal. And with signal averaging, there's some parameters here, add 20 or 50 samples over the top of each other, and you can clearly see that it's brought that way out of the noise. So that improves your detection rate. So some of the first signals, this down converter, you can see it is not really what I would call a production version. It's hung off bits of wire off the feed arm of the dish, but this was the very first experiment to receive Venus Express, which was about 6 million kilometers away. There's a phase-locked oscillator, a waveguide filter, and a mixer and some amplification. All very straightforward. This is an old Marconi satellite TV LMB that had been repurposed and tuned down a couple of gig to 8.4. And as you can see with a spacecraft so close, the signal is enormous and very easy to see in the waterfall. So the next spacecraft of my interest was MRO. This is, I would not say this is DX, 72 million K. It is fairly close in terms of terrestrial DX. It's reasonable. It's unobtainable in terms of terrestrial DX, but when you've got line of sight to the spacecraft, it's obviously a little bit easier. You can just about see the outline of the antenna and where Mars was, which are a very clear night, but extremely cold. And anyway, so here is a artist's impression of MRO. This is very nice. 100 watts of carrier to a 3-meter dish is obviously going to be quite a loud signal, even though the distance is significant. So, first signal, 10th December 2005, 72.6 million K, and you can see that is a whopping signal, just about detectable in the headphones, but on an FFT display, very, very easy to copy. Okay, so I've got a few slides. As I said, there's a number of spacecraft. I won't bore you to death with all of them, but there are a few highlights of stuff that has been received. So you can see a bit of a gallery of some of the interesting things in the past, one of which was a solar sail. This was particularly interesting because the X-band transmitter was at the edge of the sail, and when the sail was unfurled, we could, by Doppler measurement, work out the diameter of the sail, which was, you compare it with the press pack, and it comes out to within 6 inches of actual. So that's just based on radio obs. So here is a FFT from Stereo B. This is the solar observatory spacecraft that's currently broken, and it is undergoing recovery efforts, but this is on the day of launch. It's extremely close, a million K, and you can quite easily see sidebands. This would be very simple to decode because it is so close. OSIRIS-REx, so this, I don't know if you follow spacecraft in the news, but this had a gravity assist swing by very recently, and this was the signal from it, again, quite a loud carrier. Another shot of Stereo A when it's out at its operating position, so 263 million K, and this is quite nice because it's a spacecraft that is so loud you can use it as a sanity check for your DSN system, and this is very easy to copy in the headphones. So most days I point at stereo A, can I hear it in the speaker? Yes, system's working, and there's a spider hasn't moved into the feed or something like that. So I don't know if you saw the talk first thing about the Rosetta mission, very, very interesting, and about the landing. A few of us who have our DSN systems at home watched the landing from an RF perspective. You could see the carrier here on the approach to the comet, and here there's an abrupt stop, and that is the point of the landing. The nice thing about this is that you have 30 to 40 seconds of heads-up knowledge between those people watching on internet because of the codec delay and those people that are receiving it directly. So 3 or 4 of us heard it, and it was a sad day to see the carrier disappear, because this is not something you really ever see on X-band, the end of a mission. Where was Rosetta? So I'm here. The thing that we never see in this country is here, the sun, and Rosetta is about here, just to give you a perspective. Mars Express, this is a European Space Agency spacecraft on orbit at Mars. Again, this is something fairly easy to copy, and you can see the signal is quite large, but you may be wondering why the carrier steps like this, and that is purely to do with the type of oscillator which is on board the spacecraft, and it has a bit of jitter, and occasionally you see it wobble. So Dawn spacecraft, there is another lump of rock called Ceres, which is I think an asteroid, and that's about half an hour in terms of light minutes distance, so fairly far away. This was a medium length track, and you can see the wobble caused by the orbit of the spacecraft around this lump of rock. But this is an absolutely enormous signal, very easy to copy. Where is it? So I'm here, there's the sun and orbit of Mars, and it's here. So half again further away as Mars. Juno spacecraft, so this is currently operating in orbit at Jupiter. It's fairly far away at present. This was shortly after launch. You can see a wobble on the carrier. Again, the reason for this is because the feed horn, so a hemispheric coverage, the spacecraft has just been launched. It is in a thermal barrel roll to make sure the electronics are at a stable temperature, and the wobble is caused by the rotation of the dish with the feed at the outside diameter, and it not being exactly pointed at Earth. So again, quite an interesting experiment to work out the difference between Doppler max and min, correct that, average it, work out the antenna diameter. Where is Juno now? There's the orbit of Jupiter, there's the Mars orbit, and there's the Earth orbit. So it's not bad DX. So this is what the signal looks like at the moment. This is Doppler compensated and averaged. 41 minutes of light time. You can work out how far away that is very simply, but it's adequate DX. So this is Cassini. You'll be aware that the mission has ended with a dive into the atmosphere at Cassini. This is currently my all-time DX at 1.36 billion K, and this is using the 2.4 meter dish in my garden. You can clearly see the carrier and the Doppler profile. Now, this particular signal was received on the bank holiday of May this year. I don't know if you remember it. I was up at 1 o'clock in the morning, scrabbling around in the shed doing this, and it was thunder and lightning, high winds and rain, and it was not optimum weather. So I'd done a back of envelope calculation on the received signal, and had a local station reference a couple of kilohertz away, so I had a sanity check, and it was early in the morning, and I'd made a mistake, and it was out by a factor of 10 dB. So when I saw this signal here, I thought initially that can't be Cassini. It's a very, the distance is great, and I must have made a mistake, so it must be something drifting. But on-off tests proved that it was actually from Cassini, and I've been looking for this spacecraft for 10 years, so it was worth getting up. As far as orbits, you can see Jupiter is positively close, and Saturn at the time was about twice the distance away. So managed to make a recording of the FFT signal and embed it into this presentation. You can see the carrier here. What was very interesting during the reception is that you could see gaps in the carrier. And initially I thought, okay, that's very interesting. I wonder if the spacecraft is in a data mode where the power was being put into sidebands I couldn't see. In fact, you can see dips here, but the type of orbit, or the time and the type of orbit, was when the spacecraft was flying between the planet and the rings of Saturn. And what you're seeing is attenuation caused by lumps of rock between my antenna and the spacecraft. So even with a small dish at home, you can have quite a bit of fun looking at stuff on other planets. So a little bit closer to home, a few years ago, the Chinese launched 2 craft to the moon, the Yutu rover and the Chang'e 3 lander. This was a signal recorded from the moon shortly after touchdown, and it's a nice strong signal with telemetry. Shortly after it landed, there was it drove around a bit, and then there was a fault, and they had to fix it by uploading some new firmware and rebooting it. And the interesting thing is, on this diagram, the reboot happened here. So this is the normal, this is noise going into the modem on board the spacecraft, and then after the micro comes back and starts spitting out valid telemetry frames, you can see the normal data resuming. So this was very interesting. I made a post of this on Twitter, and then a fellow nerd somewhere in Russia came back and said, "You've caught a spacecraft being rebooted on the surface of the moon. Well done, that's quite an interesting thing to see." So with some of this data, we sent it to one of our IRC guys who's a bit of a DMOD nerd, and by stacking the frames on top of each other, it was possible to extract some data from the Yutu rover. You can pull out certain information from this frame, so there's a CCSDS ID which confirms that it's Chang'e 3X, which is the auxiliary spacecraft, i.e. the Yutu rover. And then there's other things which we found in documentation about the particular sync word, and you can see some telltale telemetry signs, so synchronization word, a counter, and lots of other data. We did compose an email to the Chinese Space Agency and said, can you send us the user handbook for Yutu, and in particular the telemetry guide and what bits do what, and funnily enough there was no answer. So a little bit irritating, but to be expected. So whilst watching the X-band signal from Yutu, it occurred to me that it would be very interesting to see whether you could see command uplink. So from a ground station in China, they're commanding the Yutu rover. My X-band system can be adjusted in terms of band, so I switched it down to the Milsat band, and on 7.202 gig you could see the reflection of the uplink to the moon commanding the rover. The signal was so loud in FM it was quieting, an enormous signal. It's something you would never hear on amateur EMI, even from very big antennas. So there were probably kilowatts going up at this point. So just one slide on the Kepler exoplanet mission. So this is a spacecraft which basically catalogues the brightness of various stars and does a round robin to, it looks at this star, measures the brightness, that star, measures the brightness, and then over a period of time it can work out if things are flying in front of the stars, i.e. planets, by a periodic dip in the brightness. This spacecraft is close, but it operates in the Ka band, and from a technical perspective I thought it may be quite interesting to build a converter which operated at 32 gig to see whether it was possible to detect. So 5 kilohertz of span, carrier at 32 gig, local test oscillator to make sure the system is working. This image took a month to gather, and that involved spending 2 hours per evening manually tracking the spacecraft, waiting for the signal. And I only later found out that the spacecraft points to Earth once a month to do a data download, and this literally was the final day before giving up. So the carrier appeared, and it was good Ka band DX, I would say. So a few slides about the future of my ground station. Obviously, in an ideal world, I could persuade the wife to let me have a bigger antenna and a 3 or 4 metre dish, but somehow I don't think that's going to happen. So have to optimise what I have at the moment. The plan is to design a subreflector, and that should increase the antenna efficiency a little bit, and lower the overall system noise figure, because the feed horn will be pointing at the subreflector, and any overspill will point at the sky, which is generally cold, whereas at the moment, obviously, the feed is at the centre of the dish, and any overspill has vegetation and other garden stuff. So this is a design for the profile. It needs to be machined and bolted onto the dish. The 32 gig stuff at the moment is a bit of a mess, and it needs integrating properly so it can be quickly switched out. The 26 gig system, which I built a few years ago to receive Lunar Reconnaissance Orbiter, currently listens to the Bell Hill beacon on 24 gig because it's in the passband, but I need to get the signal from the Lunar Recon Orbiter. And then the last on the list is to try a detection of Voyager and get the signal for that. We were discussing it at lunch today. That will typically involve about an 8-hour track. So the shack reference has to remain within 1 hertz over 8 hours. The antenna has to track the spacecraft properly, have to integrate all the signals, tens of thousands of samples of averaging, and you may see something 1/10 of a dB over the noise floor. But I think for Voyager, that would be awesome. So, other features of amateur DSM. The nice thing about this is the spacecraft are all going away from us. So when you've got your system optimised and you've squeezed every last dB out of it, you only have to wait a few months, and the spacecraft are further away, so it gives you something else to, a continually weaker signal to optimise. Loads of new missions are being launched, so it gives us something to look at. So recently, obviously, we've got rid of Cassini and the Rosetta probe, and Stereo B is broken. So we need a few more spacecraft, but they are coming. If you're interested in the AMSAT Mars missions, then DSN stuff can provide an excellent grounding in how you track another planet, how you calculate Doppler, what sort of things you have to take into account when you're looking at interplanetary spacecraft. And it's also quite nice to think about solar system dynamics and how things in our solar system move, and it is quite good food for thought. I try to talk to my wife about this, and I usually know when I've gone too far when she's face down in the meal, fast asleep. But then I stop talking. And finally, data demodulation and decoding is possible. So there's an amateur station in Germany who has taken stereo A data with a 7-meter dish and fed that back to NASA, which is really good. So that's the end. Has anyone got any questions? You can take a photo of this, and it has the links which are in the next slide, and a link to the Yahoo group and all that sort of stuff. It is perfectly 100% safe and etc. But for most normal people, there are the URLs, and I'll leave that up in case anyone's got a question. There we go.
Thank you very much. Is that working? Yes. Thank you very much. I, for one, found that quite interesting, although I think I'd have problems getting even a 1.8 metre dish in my garden. I don't think I'll get permission. I think planners might have a go as well, because I'm on the side of a hill, so it will be seen. Thank you very much. Any questions, anyone? Yeah, two at the back.
Yeah, great talk. Thanks for that. It's really interesting. I got a little bit confused right at the beginning when you said that you were slaving off the Madrid pointing, but then you also said you had your own pointing system. So you're just running off your own system now, are you?
Right, so the majority of the ephemeris data is computed for my home location, but the spacecraft are sufficiently far away that if I take the ASL pointing data from Madrid and apply a correction, then I can slave off an antenna there. And what that enables basically is, say for example, there's something else to do, but I want to take some DSN signals. I can, point it at a Madrid antenna and take that data, take the frequency information which is provided, and auto-tune my receiver, auto-point the antenna, and then take some screenshots automatically. So it basically enables unattended DX. So I would say 90% of the time it is local ephemeris data for my station. But, if the kids want to do something or I need to be away, but there's something I want to catch, then it gets slaved off Madrid.
Thank you, Paul. Obviously very interesting. Could you just give us some details about the dish? Looks like a petal dish. Is it a very expensive one?
So the
What's
dish,
maximum frequency?
it's a KU antenna, and it was made by NEC in about 85 for their first home satellite TV receiver. It is petals, so 6 petals. You don't really see them too often. Most of the petalized stuff now is very thin aluminium sheet, but this is quite nice. It's about 3 mil aluminium plate, fairly heavy duty. It's kept its profile. I haven't had it in use since the 80s, but when I was given it in the 80s, it was stored on a pallet in a wooden box, so it was not damageable. But it's I would say a heavy duty sat TV antenna from the good old days. Okay.
Any other questions?
As a complete newbie, how would you recommend having a go at this? What's the best route?
What's the best route? So I would say it depends whether you want to build all of the stuff or whether you want to buy it. So if you want to buy, you can go to DB6NT and buy a down converter, and with a small antenna, so maybe a 90 or a 1.2, you could fairly cheaply get on air and pick some signals from stereo A and probably Mars Reconnaissance Orbiter, and that would give you some reasonable DX over a couple of 100 million K. If you want the stuff which is further out, you really need a minimum of probably a 1.2 or 1.5 if you want to get Juno. For Cassini, I estimate based on the correct back of envelope calculations that a 1.2 would have done it. But it really depends whether you want to build the stuff or buy it.
Any other questions?
1.8 metre dish would be adequate, more than adequate.
Yeah, stuff out to about now about 800 million K with a 1.8 is easily doable, and it's I probably check Juno spacecraft a couple of times a week, and that is literally I think what HF people would say an armchair copy. So you click the dish tracker and the FFT and you can detect it in the waterfall. But in terms of Deep Space Network, it's an armchair copy. So yeah, a 1.8.
Okay. I think, any more? Don't think so. Right. Can we all say thank you in the usual way, please?
Thanks.